All right, so still resolving forces into components, part 3 this time. Read the question, try to draw it. Pay particular attention to what it says here, though. Let the vector I be parallel down the street and J perpendicular to the street. Right, pause it, draw it, pause it. All right, so there's a bit of a trick to this one. Generally, when you're drawing these things, the I and the J component are horizontal and vertical, but they're just like artificial constructs. So I and J can be literally any angle you want them to be. And if you're working on a sloped street, it's often useful to make I follow the run of our street and let J be perpendicular to that. So you just kind of turn your head on maybe on this angle a little bit, and that's how you're looking at our I and J components. So let's see. Here's my car right there. That's the car there. Is parked on a street on a slope of 15 degrees. So you can see there's a 15-degree angle right there. And we can do all sorts of maths here for our components. Be really careful here. In terms of our vectors, the car is subject to 3 forces. Weight. So weight is always straight down. Okay, that's our vector, straight down. Whether we're on a sloped plane or not, gravity works directly down. Now, a normal contact force of the road, there is our normal contact force of the road. That makes a 90-degree angle with the road itself. So there's our second vector. And then the force applied, force of the brake. Well, the force of the brake is the thing stopping the car from driving down the hill. So that's applied in the opposite direction, or just straight up the hill. So there are 3 force vectors. Now, you can see some little drawings in here. WJ and WI. That's the weight of the car in the J component and the weight of the car in the I component. This gets a little bit confusing. Like I said, you've got to turn your head on the side here to see that we're talking about I and J components. And usually weight can just be said it's directly in the J component, but because we put the I and the J component like this, it's not the case. It's sort of on that angle. So we're going to have weight in the I component and in the J component. But these aren't vectors. These are components. I'll undo those. These are components of the weight vector. So part B is to calculate the magnitude of N and F. All right, now, how do we calculate the magnitude of N and F? Well, F is going to be equal to the weight in the I component, because gravity is trying to drag my car down the hill, but the force of the applied brake force is the thing stopping it. So I'll just do a little bit of a drawing here. My F vector is going to be equal to W in the I component. And my car's not floating away into space, but it's also not burying itself into the ground. So I can say that the normal contact force is going to be equal to the weight in the J component. So that's, I'll put my little squiggles under the right things. So there's my basic ideas. If I can calculate the magnitude of Wi and Wj, then by extension, I can calculate the magnitude of F and N. And I should be able to calculate I and J because I just need to break that weight vector into its component parts. So that's just a repeat of what I wrote up there, just neater. Now the weight component is going to be equal to mass times gravity. So that's this bit here is this yellow part here, everything's yellow. This bit here is this bit here. Mass times gravity is 800 because we were told at the start that the car weighs 800 kilograms, times gravity, which is 9.8, which is 7,840 newtons. That is the magnitude of our weight vector. At this stage, you've done this enough that you should be able to pause this video and figure out what the weight is in the J component and figure out the weight is in the I component, because you now know that the total of the weight is 7,840. Pause, try, then follow. So we remember that the normal contact force is equal to weight in the J component. And to find the weight in the J component, it's going to be equal to the weight times sine 75. Now, why sine 75? Sine 75 is the angle that J, in the force, the weight, and the I axis. So that A there is 75 degrees. All right, so 7840 sine 75. So that'll give us 7572 newtons as normal contact force. Well, as weight in the J component, which is equal to the normal contact force. And finally, 7840 cos 75 will give us weight in the I component, which will be equal to that force. Now, those arrows don't look the same length, but they should be the same length. They'll be equal, which is 2029 newtons. So it's 2029 newtons are being applied up the hill as a brake force to stop the car from driving down the hill. 7,572 newtons is our normal contact force, the force that the ground is applying to the car to stop the car from falling straight down or down through the road. Okay, there is our resolving forces into components part 3. The ones on the slope are definitely the trickiest, so make sure you're practicing it.